Okay, I'll start recording. Um, as someone mentioned on the chat, so for the quiz recitation, what I was saying is that in addition to the usual two problems, there's a third problem. If you decide to, like, you can decide to do the third problem instead of one of the other two. And if the problem is just worth more points, so any extra points that you get over that, like, just gets accumulated into, isn't so it's like, in a way, it gets like, you can get extra credit from if you do the third problem. Like, I suppose the third problem is to some extent a little bit more difficult than the others, but I don't know by how much, but it still gave you like the ones that you would need to look at. If it, well, that's what I thought at first, maybe to offer it, but I think not, because I like increased the grading load of Tariq, the TA. So just to know which problems you can expect. I mean, because I did give you like the list of problems that I would use for the third problem. So and some of them do have the answers. It's just that they don't have the written solutions. But yeah, choose two of the three. So it's just to not increase the grading load. But yeah. I still, even if you don't do them, I still write the solutions for the quizzes, post them on Canvas. So you can also write the solutions for the three problems. So you can read them if you decided not to, like, you can read what it was like. So. There's still, as usual, like the YouTube video, which I don't know if you have been watching for the optional questions and the quizzes, but I think they're fun videos. So oh, good. So I'll talk to you today about the directional derivative from the gradient. Maybe just as a reminder of last time, we were doing the chain rule, and we'll use it today for a couple of nice things. So let me remind you what the chain rule said with an example. So up to this point, like, all the functions I have been writing have been functions of two variables, but basically everything that I have said can be done for functions, say, of three or more variables. Three is like the top that we will get to in this class. So let's say I give you a function of three variables, which is this one. Okay. And then I tell you that secretly X, Y, and Z depend on other variables. So X, say, becomes U squared, and Y becomes U plus B, and Z becomes U times B. Okay. And so if you think of X, Y, and Z as depending on these new variables, U and B, then implicitly F actually can be regarded as a function of U and B. So you can, like, ask, for example, to find the partial derivative of F with respect to U and the partial derivative of F with respect to B. Is that okay? Because again, there's you could do like the actual substitutions so that you would see that explicitly, but like the idea of the chain rule is that you don't need to do the substitutions directly, at least not at the beginning. So if you remember like the idea of these diagrams that I showed you last time, on the top you put like the function itself. Then below it, you put like the variables on which the function depends directly. So f depends directly on x, y, and z. Okay, and at the bottom, you put the variables on which these depend on. So x depends on u and v. Sorry, x depends on u, and y depends on u and v, and z depends on u and v. So like one option would be like to just like copy these variables multiple times, or you just like write them one time at the bottom level. So this is more convenient because otherwise you just have to keep writing UV, UV, UV many times downstairs. So you can just leave the diagram like this. So it's like a dependency diagram. And so say if you want to find, say you wanted to find the partial of f with respect to u. Again, it's almost like a game of a maze. Like you have to just ask all the ways that you can start at an f and end at u. Okay, so what are all these ways? Like, well, you can go from f to x and from x to u, right? Or you could go from f to y and then from y to u, or you could go from f to z and then from c to u. Is that making sense? So far, so good. And so there are like sort of three separate paths. So for each path, you sort of have to compute a couple of things. So, but the idea is that the partial derivative of f with respect to u is like sort of the sum of the three contributions. So for the first path, you go from f to x. So that's the partial of f with respect to x, and times the partial of x with respect to u, plus, and then you go the second path. So for the second path, you go from f to y. So that's a partial of f with respect to y, times the partial of y with respect to u. And then for the last one, you go from f to z. And then you go from c to u. Is that okay? So far, so good? Is that making sense with everyone? Any questions about this? So for each separate path, you compute the partial derivatives and multiply them, and then you just add the contributions together. Okay. And so, and then you just have to compute these like partial derivatives. And again, the fact that there are like three variables is okay. They're just found in the same way as before. So the partial of f with respect to x, what do you get? You get 1 plus z, right? Is that okay? Times the partial of x with respect to u, which is 2u. And then the partial of f with respect to y, that's just 2y. And then the partial of y with respect to u, that's 1. And then the partial of f with respect to z is x, right? And then a partial of c with respect to u, that's v. Is that making sense so far, so good? Any questions about any of the derivatives I found? And then, how did I get 1 plus z here, you mean? That's the one that corresponds to the partial of f with respect to x, right? So when you take the derivative with respect to x, you see you get a 1 from here, but you get a z from this one. Well, the thing is like y squared is being added. So this is a plus. So, you know, this one is treated as a constant, right? Because it's a partial derivative with respect to x. Is that okay? Good, good. Any other questions about this? And this is more or less the answer. It's just that, you know, this still has like a combination of x, y, and z with u and v, and you want everything sort of to be written explicitly in terms of u. So you just finish doing the substitution, like so this is 1 plus z, but z is u times v, and so this is times 2u plus 2y, but y is u plus v, so u plus v. Well, times 1, but you don't have to multiply by 1, right? And then x v, and so that becomes u squared v. And so this is the answer. Is that okay? Is that making sense? And then the other one is sort of similar. Let me do it quickly. If you wanted to do the partial of f with respect to v, it's analogous. You just have to ask all the ways that you can go from f to b. So you can go this way, the first path. Well, I mean, that one you'll see gives you 0 because actually x does not depend on v, but like we can write it like this. And then you can go from f to y and then y to v. So I'll actually say something about implicit differentiation in a moment. Yes, good. Later, maybe not right now, but yeah. And then, but it's all related. Yes, yeah. And so, and then from f to z, and then from c to b. Now, if you look at this, again, what's the partial derivative of x with respect to v? Well, that's just 0, right? Because x is actually only like a function of u. So in fact, you could skip this step if you want. I'm just writing everything explicitly so that you see it. And then partial of f with respect to y, we found it before. And then a partial of y with respect to v is 1. And then the partial of f with respect to z, we also found it before. And the partial of z with respect to v, that's u. Okay, so it's not that different. I mean, like they're sort of very similar, like the way in which you compute the partial derivatives. There's not that much of a difference between doing this one with respect or this one. Like you just change a little bit of like the expression of the function. And so 2y becomes 2u plus v, and then x again became u squared, so you get u squared times u. So this gives you u cubed. Is that okay with everyone? So that's like what you get if you simplify the answer. Okay, so that's one way in which you can take that, like this is one of the ways in which you can use a chain rule to find these partial derivatives. Here's like a very nice application of how to use a chain rule. And this is related to the topic of directional derivatives. So let me just keep writing here. Let's think of like a function of two variables, f of x comma y, as giving you the temperature at the point x comma y on that XY plane. So f of x comma y is sort of like a temperature function, because like imagining you have like a thermometer, and then you place a thermometer at a point on the XY plane, you read a number, right? Like say 50 Fahrenheit, or if you want to work on Kelvin, whatever. So you get like a number, and that's the value of the function that's at that point on the plane, right? And so as you move along on the plane, like on the XY plane, you get like different values for the temperature, and that's how you cook up your function, okay? So that's okay. And so here, so like in this, from this perspective, right? Well, let me write it here before continuing to moving. So what's the partial derivative of f with respect to x? That's sort of like the rate of change of the temperature when you're moving parallel to the x-axis, right? Because remember that on a partial derivative with respect to x, only x is changing. So this is the rate of change of temperature if you move parallel to that x-axis. And the partial derivative with respect to y is how much the temperature is changing if you just move parallel to the y-axis. Is that okay? So, but I mean, obviously you may want to move in a way that's not just either parallel to the y or x-axis, right? Like there are other ways to move on the plane. So imagine, just to make this problem simple, imagine that you have the xy plane here. And you start at the origin. So here's where you are. You're located at the origin. And say you want to move in a direction v. So you want to move in a direction specified by this vector v, right? Yeah, kind of secretly, but it is hidden, but I won't make it explicit. But so, you know, like if you're at the origin, you have your thermometer and you like this direction. And so I want to start moving in this, walking on that direction. And I want to just see how the thermometer is changing, right? Like the numbers I start getting as you move along this direction. Now, like the reason why I'm drawing this is that, you know, this direction sort of gives you a line, right, in space. So I don't know if anyone remembers like the equation of a line. It was point plus t times a vector, right? Let's call this the point P. And so what do you get for the equation of the line? You get 0, 0. I mean, because of this very specific example where the line is going through the origin, you get 0, 0 as your point plus t times this vector, right? Which is v1 comma v2, right? But those, like, this point is just like a point x comma y, right? So you get x comma y equals tv1 and tv2. Is that making sense so far, so good? So what that really means, and like this is like the whole point of the parametric equations, if you think about it, this really means that x becomes like a function of t, right? It's tv1, and y becomes a function of t, which is tv2, right? In this particular example. So it means that you can rewrite like x and y in terms of t, right? So so if you think about the diagram, right, along this line, you had this function f, right, which in principle depends on two variables, x and y, right? But then each of these variables then depend on just one variable, which is t. So in terms of the diagrams that we have been doing for the chain rule, you could like draw like a diagram like this. So this is like for along the line. So what I'm saying is that on this line, you can think of f as a function just of t, right? So let me write it more precisely here. So on this line, f can be thought of as a function of t. F can be thought as a function of t. Is that making sense? Is the diagram okay? Let me try to draw a better t. So far, so good. Because again, on the line, x and y become functions of t, right? So you can find the derivative of f with respect to t, okay? Notice that, I mean, this doesn't matter. Yes, like, I mean, right. Yes, yeah. It sort of works also for a curve. Yes. Because it's a rate of change. So yeah, it is fine, right? Secretly, like what happens is that if you have like a curve, right? The rate of change along that curve at a point agrees with the rate of change along the tangent line. So it can always be reduced to like a tangent line computation. But yeah, it will be fine. Right. So how many ways are there to for like notice that I wrote this like in the more traditional notation of like the D, not this weird curly D that I have been using, just because now there's only at the end like a single variable at the bottom. So that like that's okay, because then like you can actually think again of in terms of a function of one variable. Doesn't matter too much if you like. It would have been fine if you also write it with the curly D, but it's just more appropriate to write it like in the normal way. So what are the ways for going from f to t? You can go this way, right? So what happens here, if you get that, if you use that path, you put df dx dx dt. Again, whether you want to put like partial derivative here or not, that's fine. They sort of collapse. They mean the same because x is only a function of one variable, right? So when it's a function of one variable, there's no difference between taking like a partial derivative and like ordinary derivative. So you can write it in whatever way works best for you. Is that making sense? So far, so good. Now, what is the x dt? Good, v1. So you get this thing, and what is dy dt? v2, right? Is that making sense so far, so good? And I don't know if now this looks a little bit familiar because this is like, you know, some end like multiplication of two entry, like, you know, you had this vector v1, v2, right? And you're adding together like some things that involve multiplication, right? So which operation did we see before that involves like adding a bunch of multiplications? Yeah, the dot product, right? So this is the same, this in more fancy ways can be written as a dot product between these two things. Right, because it just gives you back the answer that I wrote before. And so this you recognize is like the vector that I called V, right? But this is a new character, which maybe you haven't seen before, and this is called the gradient of F, okay? And so this is called the gradient of F. So what we just found is that the derivative along this line is a dot product between the gradient and this vector, okay? So let me just write more in a more useful way what we just found. So let me tell you what the gradient is. This is denoted, this is called grad of F. The other way in which it's written is this way. And this is just by definition, the two partial derivatives of F, like organized as a vector, okay? So just to give you some examples. So like as an example, if I tell you that a function is x squared plus xy, what's the gradient of F? Well, you just have to compute the two ordinary derivatives, the partial derivatives, and you just write them as a vector. So what is the gradient here? It's the partial derivative of F with respect to x, which is 2x plus y. And then you find the partial derivative of F with respect to y, and that gives you x. And so the gradient is just these two things, one after the other. Like it's written like just as a vector. Okay. Or another example is that if you take a different function, which is like say x plus sine of y, then what's the gradient of this function? Well, you find the partial derivative with respect to x, which is 1. You find the partial derivative with respect to y, which is cosine of y. And then the gradient is just a vector that you create by putting like these partial derivatives together. So the gradient, oh, let me call it g so that it's less confusing. The gradient of g is just 1 comma cosine of y. Is that making sense so far, so good? How to build a gradient? Yeah. Right, good point. So for example, excellent. In fact, you can do this with as many variables as you want. But yeah, like 3 again is the most we will go. What do you think it would be the gradient of like a function of 3 variables? Is that making sense? Like that's sort of like that natural candidate for what the gradient of 3 variables should be. So for example, for this function that I gave you earlier for that we used for this first chain rule problem, let's call it f of x comma y comma z, x plus x, y squared plus xz. Right, this was like the first function that we used today. Well, if you remember, the partial derivatives were just like 1 plus z, and then with respect to y, it was 2y, and then with respect to z, it was x, right? So the gradient of f would just be 1 plus z 2y comma x. Is that making sense with everyone? Is that okay? So far, so good. So it's like you're not doing anything too wild. You're just finding the partial derivatives. And then you just put them in alphabetical order as a vector, right? X, Y, and Z. So far, so good. Yeah. Good. We're getting close to that question. We're getting close to that part. But first, one just needs to know how to find it, right? And after you find it, then you can ask what this all means, right? But for now, we're just like I actually just trying to like compute it, right? And I'm about to tell you what it means. So. But before like even telling you what it means, let me show you how it looks like. And so let's go to GeoGebra. Oh yeah. Let's do it this way. Yeah, I don't like this one. I'll do it this way. Oh yeah, good. So I don't know if you remember, like we had 2x plus for the first example that I gave you, x squared plus xy. I'm going to write it on the chat so that everyone knows which one I'm talking about. The gradient was 2x plus y comma x, right? Everyone sees that on the chat, that what I just wrote. So let's put 2x plus y. Oh, sorry. 2x plus y comma x. And that's the gradient, right? So what's going on? Like, because I wrote it as a vector, right? So the gradient is supposed to be a vector, if you think about it. So what this is saying is that what the gradient means is that at a particular point, right, you're going to draw a vector which has entries 2x plus y comma x. So for example, what would be the gradient at the point 1 comma 1, right? So that means that in this example, you're substituting x with 1 and y with 1. And so that gives you what, 3 comma 1. Is that making sense? So because again, you're so depends on what you mean, like writing it out. Sorry, I just meant that the gradient of, so if like, let me write it like again, like what I'm saying is that if the gradient for the function f comma y, we found that the is that I cannot write it on GeoGebra and like, unfortunately. So I'm just saying that this is what we have found, right? For this function, we had found that the gradient was this, right? But like this depends on x and y. So what I'm saying is that the gradient changes from point to point, right? So you can take the gradient and evaluate it at a particular point, like 1 comma 1, and you get 2 plus 1 comma 1, which is 3 comma 1. Is that making more sense? And so, but like, so what I'm saying is that if you go to the point 1 comma 1 on the plane, right, you'll see like this tiny vector, and this vector is supposed to represent um, the vector 3 comma 1. So you see it's like a little bit longer in the x direction than the y direction. So as another example, what would be the gradient of f at the point, let's see, just to make 0 comma 4, which is or 4 comma 0, which is this red dot here. What would be the gradient at 4 comma 0? Well, it means that you have to substitute x with 4 and y with 0, right? So the gradient of f at 4 comma 0, no worries, it is like 8, right? 8 plus 0 comma 4, right? So it's 8 comma 4. Is that making sense? So that means that at the point 4 comma 0, you would draw a vector which is a vector 8 comma 4. Is that okay so far, so good? And like say we had also, like, I don't know if this will work with GeoGebra because it is it involves a trig function, but we had like this function sine of y, x plus sine of y, and I told you that the gradient of g was 1 comma cosine of y, right? This was this other function. So then you can plot the gradient, and then let's see, you would put here 1, and then you would put here cosine of y. Okay, and that's how the gradient looks for this for this one. Okay, but like what I want you to think is that a gradient is supposed to be a bunch of arrows that you start drawing on the xy plane. You see? In like the way which you know the direction of the vector is because like say if the vector that you get, like before we got the vector 8, 4, right? In the previous example, we had this vector 8, 4. And so what that means is that you have to draw the vector 8, 4 at the origin. And that's like something that you should know how to draw. And then you just move it to the point where you evaluated the gradient. So you can draw the vector at the origin first, and then you shift it to the point where you're doing the evaluation to get what the answer should be. So I mean, in practice, it's not that you're going to be necessarily asked to draw gradients, because like, to get like an accurate picture, you have to draw many arrows. So that's like a lot of time. But the way in which the computer is doing it is like, you plot this vector, you draw this vector at the origin, and then you just shift it to the point where you did the evaluation. And I think there was a one on 3D, like maybe, let me see if this one works. Well, I mean, let's put it here. And then if you remember for the other example that I have drawn, before, it was x plus y squared plus xz. I'm writing on the chat right now, and we found that the gradient was like 1 plus z comma 2y comma x. That's what we had found. And so here you would put 1 plus z, and then 2y, and then x, and that's your gradient for this function. Okay.
Without actually graphing it, are you able to infer what like a regular graph of this function would look like?
Well, I mean, the gradient is not I wouldn't use the word graph, just because the gradient is what people call vector field. So the idea of a vector field is that at any point in space, you draw an arrow, right?
Right.
So here's like a vector field for you, right? And now, so the gradient itself is not like the graph of a function, right? Now, if you know the gradients, like, the things like for a function of 3 variables like this one, right? Like the graph really, it requires like a 4th dimension to actually draw the graph of the function, right? Like this graph of the function f would require a 4th axis, so you cannot really see the graph, right?
Right. It's a vector valued function of 3 dimensions. So
right. Well, I mean, it depends on, okay, so the f itself depends on 3 variables, right? But the output is a scalar, right?
Right. Exactly.
So it's like that is called like a scalar function, right? The gradient actually depends on 3 variables, x, y, and z, and it gives you an output 3 new variables, right? Like the entries of the vector, right?
Right.
So it's actually, in a sense, 6-dimensional. It requires, because it has more like the domain. The domain is like has three outputs, right?
Right.
So it's not even. It's called like that's what it's called, like a vector valued function, right? Like the gradient. But you don't try to look at their graphs in that sense. But you rather think of this as just draw on the point x, y, z. Draw this vector. Because that way you don't need to add like extra axes, if that makes sense.
So you can kind of gain inference on basically the beginning points of all of the vectors are inputs, they are not outputs. So you're kind of looking at like the rate of change in a certain direction given this input.
Yes.
Okay, thank you.
Yeah. And if and now, okay, so let me go back to the iPad so that just to summarize a little bit of what I was showing you with the animation. So the philosophy here is that, like, the point of view is that the gradient is a vector field. Okay, so the gradient is a vector field. Meaning that at a point x comma y or x, y, z, you can draw an arrow which gives you the gradient, right? So meaning at the point x, y or x, y, z, you draw a vector whose entries are the entries of the gradient. You draw a vector whose entries are the entries of the gradient of f evaluated at the point comma x comma y, evaluated at this point. So just to have like a cute picture here, if you say look at the xy plane, the easiest example to draw is like x squared plus y squared. Sorry, if you have like this function x squared plus y squared, the gradient is very easy to find. It's just 2x comma 2y. Okay, because those are just like the partial derivatives again. So like that means that again, like at a point x comma y, you draw the vector 2x comma 2y. Okay, so here if you have another point, you draw a vector here. And so in fact, the gradient, like in this particular example for this vector field, sorry, for this function looks like something like this. Like if you think about it, it's just making the position, the point x comma y, it's just like twice as big, right? It's 2 times the vector x comma y, so it just rescales the vector by a factor of 2, like the position. If this was like the vector x comma y, the gradient is just like the same vector but twice as big. You see? And so how is this all related to the question of what it means? So what we found, like the idea of a directional derivative. So a directional derivative of a function f in the direction of a vector v right? It's what I was telling you before. It's just like the idea is that this will be how much the function changes if you move sort of along the line determined by this vector, right? So it is a rate of change of f in the direction determined by the vector v. And this usually it's written like this, like this is called this is how you write this. This is the name for the directional derivative. It looks a little bit different from the other ones that we have written so far, but this is like the symbol for the directional derivative. And so just like a conceptual question before we continue. So this is like a conceptual question before we do anything else. What would be the directional derivative along the vector I? What do you think that is? I being like the vector, say 1, 0, for example, like the usual I, J, K vector. So that's the rate of change of the function when you move in the direction of the vector I, right? What was the name we gave to the rate of change of the function? How is the vector I related to the x-axis? It's like just the partial derivative of x, right? Is that making sense? Because I moving in the direction of I is the same as moving in the direction parallel to the x-axis. So it's just the same. And what would be the directional derivative in the direction of j? And if the function had 3 variables, what would be the directional derivative in the vector k direction? Good. So like basically what we're saying is like, no, we're not necessarily moving parallel to I, J, or K. We're just maybe moving like say at a 45-degree angle or a 30-degree angle with respect to one of these vectors, right? So it's sort of, if you want a picture, what I'm saying is that here you are at a point, there's this direction V, and we want to know how much the function changes by moving along that direction. So we're like interested in the rate of change along this direction. So we're trying to find the rate of change of f along direction B. Okay. And like the whole point of this thing that I did a long time ago with the chain rule, sorry, just to go back for a second. When we did this, that was to just to show you that the directional derivative, which I had not called that way before, is just really the dot product of the gradient with the vector v. So the main formula that you need to know from everything that I have said thus far is that here's the key formula. Is that if you want to compute the directional derivative, you just need to compute the gradient and take its dot product with the vector that you care about. With the caveat, like just the thing that you have to be aware is that when we use this formula, we have made like a convention where V has size 1, like has unit norm. So in this formula, so that it really use like, because like it's sort of analogous to I and J, so that it comes the right way. So I and j are unit vectors, right? So you sort of want to think of the direction as being given by like a unit vector. So in this formula, for when you use a formula, you have to rescale the vector v so that it has size 1. So you have to of norm 1. So if you were not given a vector of norm 1, you just have to divide by its norm before using it. So if you're given a vector which is not of norm 1, then really like the formula is the following. So if you want, you can think of this as being the actual formula. Yeah, it's what we call like this. This is what you like. This junk is what you would call v hat, right? This thing, yes. Yeah, it's more fancy to call it v hat, but I don't want to introduce another letter. But I'm just saying, like, if you want to think of the formula being given this way, so that you don't forget to divide by the norm of the vector. That's the only thing that you have to think about. So let's do, like, before even trying to understand this further, let's just try to do some examples so that you know how to compute directional derivatives. So let's find the directional derivative of like this function that I gave you before, f of x comma y, which was x squared plus xy. At, in the direction of the vector okay, evaluated at the point 2, 2.
Two x plus y comma y.
Oh, right. Yeah. That's the gradient you're saying, right? Yes, the gradient was this is like the one that we had found before, right? It was 2x plus y comma comma x, right?
Yes, my mistake.
No worries. Yeah. Good. So this was a gradient, and then like you just regurgitate the formula. So the formula for the directional derivative is just the dot product. Sorry, let me call the gradient just like the usual. This is like the usual notation we will use for the gradient. So it would just be the dot product between the gradient and the vector v divided by its norm. Okay. So it's not too bad. So you get 2x plus y comma x dot 1 root of 3. And what's the norm of the vector 1 root of 3, that's always the square root of 1 squared, right, plus root of 3 squared, which is you 3. Right, so it's going to be the square root of 4, which is 2. So this would be in the denominator, in the numerator, you get, when you do the dot product, you get 2x plus y plus root of 3x, and this is 2. Is that okay so far, so good? Any questions up to this point? Does this calculation make sense? And so what this is telling you is that if you are at a point x comma y, this is saying at the point x comma y, this is how much the function changes if you move in the direction determined by this vector. So it's sort of giving you like the formula for the rate of change at any point x comma y. So this is telling you the rate of change. This formula is the rate of change of f at at the point x comma y in the direction of the vector 1 root 3. So like at different points on the plane, the rate of change when you move in this direction varies according to this formula. Okay, and so if you just want the rate of change at the point 2 comma 2, you just evaluate plugging x for 2 and y for 2. So the directional derivative of f in the direction of v at the point 2 comma 2 would be 4 plus 2 plus 2 root of 3 over 2. And this would give you what? 3 plus 3 root of 3. Is that okay? Is that okay? So you see, finding the directional derivative, it's reasonably okay. We can still interpret this a little bit more. So let's talk a little bit more about the interpretation. So again, let me draw the picture on the XY plane. It's similar everywhere else. I mean, you could also do it with XYZ, but like, so what I'm saying is that if you have a point x comma y, you can move in the direction given by a vector v, right? And you could also, and you see like at the point x comma y, we also have another vector, which is this gradient vector. So we also have in general this gradient vector. Right. And there's usually these two vectors are not aligned, right? They don't necessarily, I mean, because v is just like a random vector. So there's usually some angle between, there's some angle between the gradient and the vector v, right? And so if you think of the formula of the directional derivative as being this one, I don't know if anyone remembers the interpretation of the like dot product. Does anyone remember the interpretation of the dot product in terms of the angle?
Norm of u times norm of v cosine theta.
Yes, yes. So it would be the norm of this vector, right? Times the norm of the other vector, which I'm writing like this. times the cosine of theta, right? Now, what's the norm of the second factor? What is the norm of this? It's 1 because like you sort of did this so that it would be rescaled to have size 1. So really this is 1. All of this is just 1. So what you find is that another formula for the directional derivative is just the norm of the gradient times the cosine of the angle, or here theta is the angle between v and the gradient, right? So here theta is the angle between v and the gradient. Now, why is this nice to see? Because this is something that should be familiar from the squeeze theorem or the sandwich stuff. I mean, someone asked me, right, squeeze theorem or sandwich theorem or ham theorem or whatever, like, I think there's something like that. I mean, they're all called like, they're synonyms. I don't know. There was like, when we were doing all these squeeze theorems, there was always like a property of cosine and sine that we always use about their values. What can you say about the value of cosine of theta? So it's between what?
-1 and 1.
Right. So that means that the directional derivative, whatever it is, the biggest it can get, what's the biggest size it can take? It can become as big as the size of the gradient, right? And how small can it become? It can become as small, I mean, it can become as, like the biggest size is happens when cosine of theta equals 1, right here. So this is when cosine of theta equals 1, right? And the smallest it can become, or the most negative it can become, is when cosine of theta becomes -1, right? Is that making sense? So the directional derivative is always between two numbers, which are the value of the gradient, like the size, the norm of the gradient, or minus the norm of the gradient, right? Now, when is it that the angle between two vectors? I mean, if we're saying that the cosine is 1, when is the cosine 1? Is when the angle is 0, right? So that means that the vector v had to be parallel to the gradient, right? So this happens precisely, this case happens precisely when a v and the gradient are parallel, right? Because that's when their angle is 0. So this is when v and the gradient are parallel. Because that's when the angle is 0, right? And when is the cosine of theta equal to -1? What do you need the vector and the gradient to be like? They need to, I mean, they need to point in opposite directions, right? So v has to point in the reverse direction, or like it's anti-parallel. Like, let me put like a picture here. So like what I'm saying is that this situation happens whenever you have the vector v like this, and here you have the vector, the gradient vector, and this one happens when is that making sense? So just to summarize, what I'm saying is that the maximum value that the directional derivative can take is the size of the gradient, and this happens in the direction determined by the gradient. So the maximum rate of change is equals the size of the gradient, and the minimum rate of change, or the most negative rate of change, like that's a way to think about it, like the most negative rate of change, or like largest. Okay, let me put it like this, like the largest increase, right, of f. So the largest increase, which is another way of saying the like the maximum rate of change, the largest of increase of f is equal to the gradient equals the gradient, and that's in the direction determined by f. Sorry, in the direction of the gradient. And the largest decrease, right, the most negative it is, that's minus the value of the minus the norm of the gradient, and that's in the direction determined by minus the gradient. Okay. So so if you think of one interpretation of this fact is that if you think of your you have a function of two variables, like here's a cute interpretation. Think of your function of two variables as representing, like, again, like the height of a mountain. So maybe the graph looks like this. So it has like a valley, you know, and has like a peak. So if you want to move in the direction of steepest ascent, right? If you want to increase your height as much as possible, you have to move in the direction determined by the gradient. And if you want to move in the direction of steepest descent, you have to move in the direction of minus the gradient. So the direction given by the gradient is the direction of highest ascent or steepest ascent. So and the direction given, gradient of h. And the direction given by minus the gradient is the direction that you would need to move in if you want to decrease your height as much as possible. So this is like steepest descent. Is that making sense? So far, so good. And I'll repeat this next time because we only have 5 minutes, but like just for the idea to start sinking in, let's think about the level curves, right? So back to our friends, the level curves. So again, imagine that the function was h of x comma y. This is like the height of the mountain. Right? So what was the level curve in this case? A level curve maybe would look like this. Right? What would, let's say this is like the level curve h of x comma y equals 10, right? What does that mean? This these are all the points where the height equals 10, right? Like all the points where you would see the mountain have height equal 10 miles. Well, that would be too much, but right. So here's where the height equals 10. Is that okay? So what do you think, right? Imagine that you're moving, right? Imagine that you're moving, you're walking along the mountain, right? So imagine that you're moving in the direction that's tangent to this level curve, right? So this V is like tangent to the level curve. If again, like just imagine like you're like a cartographer or whatever. If you walk where the mountain is, if you move on a path where the mountain is precisely 10 miles high, what's the rate of change in height that you record? Zero, right? Because like the height is constant almost by definition on the level curve, right? Because height is constant on a level curve. Is that making sense? So since the height does not change along a level curve, if you just move along this level curve, you don't measure any rate of change. So the rate of change should be zero, right? But really, how can the rate of change be zero? It can only be zero if the dot product between the gradient of h and this vector is zero, right? Because that was the formula for the directional derivative. And so this can only happen if the gradient has dot product equal to zero with the vector v. And when do two vectors have dot product equal to zero?
When they're orthogonal?
They are perpendicular, right? So that means like, so that means that the gradient is perpendicular to the level curve. Okay, and I'll show you this next time again. So that means that the gradient, this thing is a vector perpendicular to the level curve. And this is like, again, we'll do this next time, but like, sorry, like what that means is that essentially the gradient will look something like this, and here it will look like this, and maybe here it looks like this. So the gradient is always orthogonal, like the way to say it is that orthogonal, gradient is orthogonal to level curves. Okay, and we'll use this next time for like a slightly more complicated version, which is like for when the function is 3 variables, because then we had level surfaces. I don't know if you remember, for functions of 3 variables, you could talk about level surfaces. And so that means that the gradient would be a vector perpendicular to the level surface. And that's precisely what you need if you need to find like a normal plane, because the equation of a plane requires a normal vector. So the gradient will be our candidate for normal vector. And so that's how we'll find the equation of the tangent planes. So next time we'll talk about tangent planes and use that to find like max and min of functions. Okay, so it's almost the last topic for the exam. We will be done with it, most of it on Monday, and maybe on Thursday, then we just have time to do some examples, more practice problems. Okay, but yeah, I'll see you on Monday. So have a good day.
Thank you.